So welcome back, guys. Let us continue our discussion of refresher or quantum mechanics. A few of the quantum mechanics principles which are required to understand individual motion of individual spin using quantum mechanics. So in that we were discussing angular momentum. So now today let us look at angular momentum eigenstates and eigenvalues. All right. So let us first look for Lz. So eigenstates of Lz may be specified by two quantum numbers. One is L, another is M. So for L equal to 0, M will have 0, as we all know. So for L equal to 1, M will take three values, M minus 1, 0, 1. For L equal to 2, M will take 5 values, minus 2, minus 1, 0, 1, 2, and so on, right? So Lz thus the eigen states will be defined by, instead of one, two quantum numbers, right? L and M. Okay, so it is written like this, where this is the eigenstate of Lz and Lz. As we all understand, the eigenstates will be orthonormal and they will obey the following relation. So if we operate Lz onto one of the eigenstates, we should get back the quantum number M with the plus sign and the state back. Okay, where M is this quantum number, which is called as azimuthal quantum number. It is, in some books, it is also called as projection quantum number. And this is a integral in case of angular momentum. If you consider spin angular momentum, this can also take half integral values. We all know that. Also for total square angular momentum operator. So for total square angular momentum operator, basically we are talking about L square, which is defined by Lx square plus Ly square plus Lz square. It will have same eigenstate Lm with different eigenvalues, L into L plus 1 and the state back. Okay, so in this case L defines the total square angular momentum and M defines the angular momentum along z-axis. That's why it is also called as projection quantum number. So what we can say is L defines the total square angular momentum, because it is coming in coming as an eigenvalue of total square angular momentum operator, and M defines the angular momentum along z-axis, or any given axis for that matter. Okay, so now let us look at how to find out matrix representation for Lz operator, and then we can work out for L square operator also. So for Lz operator, let us say if we are talking about L equal to 1 state, we will have 3 by 3 matrix, because it will be a the number of states will be 3. So let us first write down what are the number of states. So L equal to 1, so M equal to 1, L equal to 1, M equal to 0, and L equal to 1, M equal to minus 1. Okay, now same here it will be in this fashion. Okay, so now if you, so this is 1 1 1 0 and 1 minus 1. So now you understand that if you want to calculate this matrix element, what you have to do is you have to take these two states and put in the LZ operator, apply LZ operator, and whatever the eigenvalue comes here, that will be placed here. So that means this is the kind of matrix or kind of integral that will be set up here, right? So now here these two states are same states, so that's why the integral will not go to 0, because I'm saying this because these are orthogonal states or orthonormal states. So for example, if we are talking about, let's say, two different states, 1 1 here, sorry, this is not expectation value. So if we are talking about, let's say, LZ applying on 1 0, so we are trying to find out this matrix element, let's say, no, this matrix element, let's say. So here the state will be 1 0, and on the ket side, bra side, it will be 1 1. So the integral of these two, because these are orthogonal states or orthonormal states, this will go to 0. So we can straight away write the matrix element as 0 when the two states are not same. So similarly here it will be 0, 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 right? So these 6 terms will go to 0 straight away. Now let us try to find out what will be the matrix element over here. So LZ operating on L comma M will give you, this will be 1, and the value here will come out to be plus 1 1 comma 1 and the state back, right? So this 1 can go outside and this integral will go to 1. So you will have 1 over here plus 1, which is the eigenvalue of LZ operating on 1 1 state. Similarly, eigenvalue of LZ operating on 1 0 state will be 0, and here it will be minus 1, right? So LZ in LZ operator matrix representation can be written as 1 0 0 0 0 0 0 0 minus 1, right? So similarly, as a home exercise, you can calculate the matrix representation for L square for let's say L equal to 1 state. Okay, so this will be again a 3 cross 3 matrix, and whatever the value comes, so find out the value, and we can discuss during the interaction session. Alright, so remember that the LZ here is a Hermitian operator, and thus the real eigenvalues are coming along diagonal, and all the off diagonal elements are 0, right? So that's another indication that this is a Hermitian operator. Okay, so now for Lx and Ly, so let us also calculate for the matrix elements for Lx and Ly operator. So Lx and Ly operator do not commute with Lz, and the matrix representations are not diagonalized in Lz eigenbasis. Also, mathematically, it is more convenient to work with shift operators, ladder up and ladder down operators, to define Lx and Ly. So let us define what is L plus. So L plus operator is defined as Lx plus minus so plus I Ly, and L minus operator is defined as Lx minus I Ly. Okay, so from here you can calculate the value of Lx. So Lx is nothing but L plus, so if you add the 2 and divide by 2, this will become Lx plus L plus plus L minus divide by 2. Similarly for Ly, it becomes L plus minus L minus divide by 2I, right? So from once you know L plus and L minus operator, shift operators, then you can calculate Lx and Ly. So let us, it is easier that way, otherwise there is no reason to define shift up and shift down operator. So mathematically the calculation becomes much easier. Now the eigenvalues for L plus state, let us say the L plus is also operating on Lm. The value is given by L plus 1 minus M plus 1. Okay, and then the square root. So this is the eigenvalue for Lm state, and because it's a shift up or ladder up operator, it takes the M value to a higher state. So that is, it leaves the state changed to M plus 1 state. So from M state, if you apply L plus operator on M state, you land up at M plus 1 state. Similarly for L minus, you have Lm and L plus 1 minus M minus 1, and you land up at M minus 1 state, right? So that is easy to see. So shift operators increase or decrease the M quantum number, and thus eigenvalues would also appear accordingly. They won't appear along the diagonal. We will see that. So let us calculate it for L plus operator, and L minus operator you can do it at home. So for L plus operator, if you want to calculate for Lm, where L equal to, so we will have 3 states here again. So we have 1 1 1 0 and 1 minus 1. So here also you have 1 1 1 0 and 1 minus 1. Okay, now if you see that if I'm operating onto this state 1 1 state, then I land up at a higher state. So higher state will be from 1 I will go to 0, right? So that means if I'm now taking the integral between these two states, it will come out to be 0, right? Similarly, if I'm taking an integral between these two states, it will come out to be 0. So so now that you understand that how to calculate different matrix elements, why don't you take it as a home exercise and find out rest of the elements also. Also do it for L minus operator. This is simple and straightforward, so you should be able to pull through. So this will also be a 3x3 matrix, so take this also as home exercise. Okay, so now let us also consider the spin angular momentum operators. So it's spin angular momentum operators. So far we were discussing angular momentum operators. So spin angular momentums are also given by exact same relations as discussed for angular momentum operators. They will also have, so we'll not go into details of the expression, so they will have similar expressions, just that the signs are now different or the symbols are different. So this is the 3 components along x, y and z define the total spin angular momentum. Also they will have the same commutation, cyclic commutation relation as for angular momentums. So we'll write the same thing, Ix, Iy. So you saw that, right? Lx, Ly gives you minus I Lz. So here Ix, Iy gives you minus I Z. Okay. So spin quantum state is also defined by 2 quantum numbers I and m. So for I equal to 0, you have m equal to 0. For I equal to 1, you have m equal to minus 1 0 1. For I equal to half, this is for spin half system. Now this spin half systems do not come in angular momentum, they only come in spin angular momentum. So m will be minus half plus half, right, and so on and so forth, right? So if we now write down the eigenstates for Iz operator, let's say I will be writing it as IM, and what I get is plus M IM. So state back and M spin quantum number, azimuthal quantum number comes out. Also the shift operators here have the same meaning. I plus gives you is equal to IX plus IIY, and I minus is equal to IX minus of IY. Okay, and thus you can calculate IX is equal to I plus I minus 1 by 2, and IY is 1 by 2 I plus minus I minus, right? Okay. So also the rotation operators, as we discussed for angular momentum, here also the rotation operators follow the same relation. So I will just mention that here. So Rx beta is equal to exponential of minus I beta Ix, and the rotation sandwich also have the same relation. So Rx beta Iy Rx minus beta gives you Iy cos beta plus Iz sin beta, right? So this is exact same thing, so we are not discussing it again. Okay, now let us try to write down the matrices for spin half quantum number. So again the formula or the method remains the same. So for if you know the eigenvalue, you know what integrals are to set up, you can calculate the matrix elements. So for spin quantum number half, we have two eigenstates with m values of m equal to minus half and m equal to plus half. So these are, if you want to write down, you can. Okay, let's go to next page. So the two eigenstates can be written as, for spin half system, as Im, where I is plus half and plus half, and the other state is plus half and minus half, right? So this is for convenience, this is termed as alpha state, and this is termed as beta state, right? Okay, so now to write Iz operator, again you'll have to consider 2 by 2 matrix in this case. So you will have alpha state, beta state, alpha, beta. Okay, so here if you calculate the matrix element, you can calculate it by setting up the integral alpha Iz alpha over here, and whatever comes over here you can write here, and that will give you the matrix element. Also here alpha and beta states are again orthonormal, so whenever you encounter with alpha, this will be 1, and whenever you encounter with alpha beta, this will be 0. So accordingly these matrices are straight away 0. You will get plus 1 here and minus 1 here because of the m value. So if you apply Iz over plus alpha state, you will get plus half state, you will get half outside, and similarly if you get if you apply Iz on beta, you will get minus half over here. So basically Iz can be written as minus half 1 0 0 minus 1, right? plus half, sorry, here, right? So similarly, Ix, Iy, so this you have to first calculate I plus and I minus operators, and from there you deduce what will be Ix operator and Iy operator. So I'll tell you the answer for this, but take it as a home exercise and try to calculate for spin half system all four operators. Okay, matrix representation for all four. So Iz I have already given, so let's also write down for Ix. Ix will be equal to 0, half, 0. Of course you can take half outside and then it will be 0, 1, 1, 0, and see if your answer matches to this. Iy is equal to 1 over 2i, 0, 1, minus 1, 0, and let's also write down I plus. So I plus will be 0, 1, 0, 0, and I minus will be 0, 0, 1, 0. Okay, and let me know if there is any mismatch in the answers, then we can discuss. Okay, so while we are discussing these operators, these matrix representation for operators, let us also define unity operator. So unity operator, as from the name, you can, in some books you will see 1 cap, or in some books you will see E cap, both are same, and as is clear, so this will be all diagonal elements will be 1, and dimension here will be 2 cross 2 because we are dealing with spin half system and there are 2 eigenstates. So now that we have defined unity operator, let us also define one more operator called as projection operator. All these operators will be useful when we are doing actual single spin rotations and all. Okay, so projection operator is defined as I alpha is equal to half of unity operator plus I plus operator. Sorry, this is Iz operator. We'll see why it is called as projection operator. Similarly, I beta operator is defined as half of unity operator plus, no, this will be minus Iz operator. Okay, so now this gives you, so you can easily calculate once you have the matrix representation for unity operator and for Iz, you can easily calculate what will be the matrix representation for I alpha. So this will be 1, 0, 0, 0, and similarly for I beta this will be 0, 0, 0, 1. Okay, so let us say why this is called as a projection operator. So let's say that you have a superposition state defined as psi C alpha alpha plus C beta beta. Okay, so it's a superposition between alpha and beta. Now in alpha beta eigenbasis, psi can also be written as matrix of C alpha and C beta, right? This is in alpha beta eigenbasis, right? So now if you apply a projection operator onto the superposition state, so this will be 1, 0, 0, 0 C alpha C beta, and what you are going to get is C alpha times 1, 0, which is nothing but C alpha times alpha state, right? This 1, 0 is alpha state. That means if you apply this matrix onto a superposition state, you get projection of that state onto alpha state. So that it is not giving you a pure alpha state, it is giving you alpha state multiplied with certain constant. That means you are projecting the state onto alpha state, and that is the projection of that. So it has removed the beta part of psi, and only retained the alpha part, right? So that's how it is called as projection. Similarly, if you operate, you can try at home. So if you operate I beta onto psi, what you will get is the C beta part, right? Okay. So let us also consider these operations, how to write these operations in bracket notations. So I alpha can be written as inner product of alpha alone. I beta can be written as inner product of beta. Similarly, the step up operator or ladder up operator, I plus operator, can be written as inner product of alpha to beta, and I minus can be written as beta to alpha. Okay. Now given that these operators are given to you, we can define Ix operator. We already know that Ix operator is equal to half of I plus I minus. So now if you calculate this, what will be the Ix operator in bracket notation? Solve it for yourself and see if you are getting correct answer. So I won't give you the answer here. So let us discuss the answer in interaction session. So calculate Ix in bracket notation using this relation. Similarly, Iy we all know 1 by 2i, I plus minus I minus. Okay. Now similarly, Iz is half of Iz can now be defined as, based on definition, I alpha, the way we have defined projection operator. So from there it can be deduced that Iz is equal to I alpha plus I beta. Now this will be minus actually, yeah. This will be minus, and the unity operator now. So unity operator can be defined as the summation of this, I alpha plus I beta. Okay. So let's calculate this in terms of bracket notation, and that finishes up the basic operator introduction or basic quantum mechanics introduction, which is required to understand rest of the discussion that we'll be carrying out. And that is all for today. Any doubts, let us discuss in the interaction session. Thank you.